Okay, hello everybody. I want to start off by asking you a question. How many people in this room can read what's on this slide? Let's see a show of hands. Oh, more than I thought, a couple. If we transcribe this into the Roman alphabet, we have konnichiwa Cádiz, so maybe you might be familiar with the phrase konnichiwa. And don't worry, this is the last time that I'm going to test you on your Japanese knowledge, so you can relax. And if we translate this into English, then we have hello Cádiz. And then into Spanish, sorry about my pronunciation, but we have hola Cádiz. Okay, and what we have here is a very simple example of a rewrite system. And a rewrite system is something which takes a structured input and systematically transforms it into something else. So in this case, we're going from Japanese characters to Roman alphabets to English to Spanish, which brings me to the title of my talk, which is Cracking the Codes, Translating Japanese Numbers with Rewrite Systems. But before I dive into what exactly I mean by rewrite systems and all that, you might be wondering why exactly I'm interested. Well, there was a kind of a spoiler in my introduction, but you might be wondering why I'm interested in Japanese translation. And actually, I am a career changer. So I did a degree originally in a very unique combination, which is maths and Japanese. And then after I graduated, I lived in Japan for 7 years, where I was a Japanese translator, mostly doing financial stuff, but also PR, corporate things. No anime and manga, nothing for fun. And then in 2021, I transitioned to software engineering. And when I was a translator, we often had to use certain types of software, which I found very frustrating. So I wondered if I could use my newfound programming skills to solve some of the issues that I used to have as a translator, which is what I'm going to talk about today. And so I don't have a clicker. I had various technical issues, so I had to keep going back to the laptop. And also, this is a picture of my brief-lived Japanese TV debut. So that's me, my head superimposed onto a cartoon body, and a Japanese celebrity reacting to me talking. We can talk about it later at drinks if you like, but that is me in Japan. Okay, so today, first of all, I'm going to start off by explaining the issues that I had with translating Japanese numbers, and then I'm going to use an arithmetic example to illustrate what a rewrite system is and some of the core concepts, and then I'm going to use Scala to implement a rewrite system for converting Japanese and English numbers into a common format. So, what were the issues that I used to have? So, as translators, we have to use a certain type of software called computer-assisted translation. This is not machine translation. It's just a kind of software that's supposed to make your life easier as a translator. And this is abbreviated to CAT tools, by the way. I'll refer to that later. And they're supposed to make our lives easier in various ways. And one of the ways in which they do this is quality checks before we submit a translation to the client. However, let's take a look at a screenshot from a CAT tool. So this is actually a perfectly translated sentence. There's no errors in this sentence. However, you can see on the left, there's like 6 different number errors that have been pointed out by this supposed quality check. And so let's take a look into why that is. So probably the most simple example of how the differences between representing numbers in Japanese and English would be a month. So in Japanese, a month is just a number plus this character, which is pronounced gatsu, but it means month. So for example, if you want to say January, you can say 1 gatsu or 1 gatsu, and February would be 2, etc. So what happens when the CAT tool sees this correctly translated as January, it's going to complain that there's a missing number. So in this example, we have here, this means September, but the tool is complaining that there's a missing 9. The next difference would be years. So Japan mostly uses like Western years, like 2024, but they also have their own unique year system, which is the imperial year system. So every time a new emperor is enthroned, like a new era starts. So for example, we're currently in an era called Reiwa, which started in 2019, when a new emperor came to the throne. And so for example, the current year is Reiwa 6, is 2024. However, if you correctly translate Reiwa 6 to 2024, it's going to complain. It's going to have 2 complaints. One is that there's a missing 6, and 2 is that there's an extra 2024. And the third difference is just numbers themselves. So there's various ways in which numbers can be expressed in Japanese text. So the first way would just be Arabic numerals. That's a perfectly valid way of expressing a number in Japanese text. The second would be kanji, which is Chinese characters. So here we have 1, 2, 3. Conveniently, they look a lot like what they represent, but sadly after that, that's not the case. And then there's a combination. So this is often used for like a large number. So you'll have like an Arabic numeral followed by a unit. So here we have this character sen, which means 1,000. So here we have 3,000. And also one further complication is that Japanese uses different units to English. So up to 1,000, so 10, 100,000 is the same. But then after 1,000, the next unit they have is called man, but it's 10,000. And then after that, the next unit is 100 million. So for example, this character, 10 followed by 10,000 would be 100,000. But if you translate that, the cat tool is going to complain that there's missing number from the source and there's an extra number in the translation. And also one other aspect of Japanese text that's sort of worth mentioning is that it's quite hard to parse Japanese text because they don't use spaces. So in English, like if you have a sentence, like a string, and you want to split it into words, you can just split on a space and you easily have a list of words. But in Japanese, you can't do that. So as I saw, most of you cannot read Japanese. But here we have a Japanese sentence, and I'm sure that nobody here, or only a few people here, can tell me how many words are in this sentence. But actually, like, they would be split kind of like that. So that's just one further sort of complication of working with Japanese text, is that there's no spaces. So you can imagine my struggle. Basically, the cat number tools are basically useless. Almost all of the errors that they produce are false positives. And it's very easy to make a careless mistake, especially because of the difference in unit. So, like, especially as a translator, like, you're not a mathematician, or maybe I am, but anyway, jokes aside, like, for example, if you've been translating for like 5 hours and suddenly you're like, oh, what's 335 times 100 million? Like, it's very easy to like be off by a factor of 10. And it's actually very important to get the numbers correct, because I was often doing financial translations. So if some big Japanese company in their quarterly report has their profit off by a factor of 10, obviously it's going to be a massive issue. So it's really important to have an accurate number check. And I mean, as you saw, like just that one sentence, there were 6 errors. And before submitting a translation, I would have to go through each and every one. So like imagine like a 50-page document. I would sit there sometimes for hours, just click, click, click. So I was very frustrated with this problem, and I wanted to solve it. So what I'm trying to achieve is, let's say we have the sentence from before. I want to be able to convert that into a common type like this, which can be a lot more easily compared. And that's what I'm going to try and do with my rewrite system. So now let's talk about rewrite systems. So basically, a rewrite system is a set of rules for transforming one term into another, and it consists of a series of rewrite steps. And a rule is basically structured this way, and the left-hand side is the pattern that we want to match, and the right-hand side is the output that we want to produce upon a successful match. So, for example, a really simple example of a rewrite rule would be x plus 0. We can simplify that to x. That's a very simple example of a rewrite rule. And I'm going to take a detour slightly from the Japanese number issue, just to use quite a mathematical example. But this, I'm going to use this example because it illustrates quite well some of the core concepts of rewrite systems. So this is symbolic differentiation. And as far as I'm aware, functional programmers are quite a mathematical crowd. So I'm sure that many of you are aware that if you differentiate x squared with respect to x, you get 2x. Let's look at how we can do that using a rewrite system. So if we wanted to make a rewrite system for symbolic differentiation, we could firstly make a rule that if we differentiate x with respect to x, we're going to get 1. And then y with respect to x, we're going to get 0. And then we have the addition rule for addition and the multiplication rule. So let's try applying these set of rules to the x squared example. So we'll start off with x times x, so this is x squared. And then we are going to apply rule 4, which is the multiplication rule, because we have x times x, and then we end up with this output. And then we apply rule 1 firstly to the left-hand side, and we get x times 1. And then we apply rule 1 again to the right-hand side, and we get x times 1 at x times 1, which is 2x. And we could probably make it an extra rule to then simplify that to 2x, but basically we've achieved our desired output. So I want to explore some of the core concepts of rewrite rules. The first one is termination. So this concerns the question of whether or not we always reach a final stage where no more rules apply. So if we do, this rule is called terminating, and the form that we arrive at is called the normal form. And the example we saw on the previous page, it was terminating because we reached a final state where no more rules can be applied. But to give an example of a non-terminating rule, we could have something expressing the commutativity of addition. So u add v rewritten to v add u. If you could just keep on applying that over and over again. So if you apply that to 1 add 2, you get 2 add 1, 1 add 2, 2 add 1. So we want to avoid doing anything like this in our rewrite system. We want all of our rules to be terminating, eventually converging to some normal output. And the second key concept, and I'm going to talk about this later because it was a problem with my implementation, but confluence. So if there are different ways of applying the rules, do we always get to the same output? So let's look at that previous example again. So first of all, apply rule 4, but remember we applied it first to the left-hand side, but what if we applied it to the right-hand side and then to the left-hand side? Well, as you can see, we end up with the same output, even if we apply the rules differently. And this means that this rewrite system is confluent. And to give a contrasting example, let's look at a non-confluent system. So let's say we add an extra rule, which is x plus 0 is x, and then we look at this expression here, the derivative of x plus 0. So there are different ways in which we could apply our rules. So we could, on the left-hand side, we could simplify x plus 0 to x first, or we could do the addition rule, and then we have two different ways of doing it. And then we apply rule 1, but then we have no rule which concerns what we need to do with the derivative of 0 with respect to x. So this is our final output, and this is different in both cases. So this is no longer confluent. And in order to make this confluent, we then need to add an extra rule, which is that the derivative of 0 with respect to x is 0. So basically, we want our rewrite system to be confluent. It generally makes it a lot easier to work with, and we'll see the issues that I had with that later. So yeah, essentially, a rewrite system is a set of rules for transforming input into output. And there are two core concepts which are quite important. One is whether or not it converges to a normal form in a finite number of steps. And the second one is whether the result is the same regardless of evaluation strategy. Okay. So now let's look at actually implementing a rewrite system in Scala. So before we looked at an example of arithmetic, but this is a case of named entity recognition, which is a natural language processing task which concerns extracting information of interest from text. So in this case, we're interested in extracting numerical information from text. And a rewrite rule consists of two main parts, which is the input and the output. So in our case, we're going to start off with a sentence, but it's going to be easier to use a list of characters. So our input is going to be a list of characters. And then our output, because we also have like some irrelevant text, like I would like, and that's not going to be rewritten. So our output is going to be using the union type of character and the entity. So we'll have a list which is mixed, and then only the numbers are going to be converted into the entity format. So let's look at how we're going to do this in Scala. So first of all, we're going to make a rewrite trait, which has an apply method, which takes a list of an input list of the type that we saw before, and then it's going to return an option. So if the rule matches, it will return sum with the rewritten text inside of it, and if it doesn't, it will have none. And then also, because we're not just going to have one rule, so we need to have some way of combining several rules. So we're going to have an or else method, which will be able to chain several rules, and then if that rule doesn't match, it will check the next one, and so forth. And then we're going to have a companion object, which has a lift method, which has a partial function that describes the pattern that we're going to look to match. And if it matches, then we're going to convert into we're going to create a new instance of rewrite with the new output. Okay, and now we need to actually implement a method for applying the rewrites to text. So this rewrite method, it will apply the rule to the text, and as we saw before, that's going to return an option. So if it's none, i.e. the rule doesn't match, then we're going to leave the head of the list unchanged, and then we're going to rewrite the rest of the list. And then if it matches, then we're going to replace the head of the list with the rewritten version, and then rewrite the rest of the list until we reach the end of the list. So let's look at actually implementing a very simple rewrite rule for our case. So the most simple case would be just a digit, an Arabic numeral digit. So first of all, we're going to make it an algebraic data type entity. And then our first case of that would be number, which takes a value. And then we're going to define some rewrite rules. So for example, if we see the character 0, we're going to replace that with number 0 and then go on to the rest. And then we're going to chain these rules with the or else. And yeah, and then it goes up to 9, but it's not shown on the slide. So let's see, applying the function to this sentence, what happens? We get a transformed text. But what about if we had a larger number, larger than 10? What if we had 12,345? Well, unfortunately, we have no method yet for actually combining the numbers, so we're just going to receive a list of numbers. So we want to actually be able to combine the numbers. So the next rule that we want to write is a rule for combining multiple digits. So we're going to create some logic for if we have a number followed by a number, how are we going to combine them? And then we put this into this rule. And then if we try applying it to the text, we still didn't combine the numbers. And the reason why is because our rewrite function, currently it only rewrites the text one time, but we want to keep looping through the text and keep rewriting until no more rules apply. So the final piece of our puzzle is this iterate method, and this builds on the rewrite method, and it keeps applying it to the text until there are no more changes to the text, and then we are left with our final result. So now let's try applying that with our chained rule. We've got single digit or else multi-digit, and let's see what happens. So firstly, it converts them to the single digits, and then in steps, it combines each digit with the one next to it, until we reach our final result. Okay, so that's Arabic numerals. So what about some of our Japanese cases? So probably the most simple one is month. So you might remember that a month is just a number followed by the character, which means month. So the rewrite rule for this is very simple. First of all, we're going to define a new case class for month, and then simply if we have a number followed by this character, it's going to make a month. And then for years, it's also quite a simple implementation. So any year in Japanese will be followed by a word which means year. So first of all, we'll have a rule that if a number is followed by year, then we convert it into a year. And then if it's one of the Japanese imperial years, it will also have a prefix. So for example, we have Meiji era here. So if we see Meiji era followed by a year, then we'll convert that into the respective year. And then let's trying to update my software. So let's try applying all of our rules so far to this Japanese text, which is a date. So we have Heisei year 3, month 5, day 13. So let's see what happens when we apply our system to this. So first of all, we convert the numbers into numbers. We're combining multiple digits. The month is correctly identified. And firstly, it goes to year 3, and then it combines with the Heisei era to give 1991, and then we end up with 13th of May, 1991. Okay, but these so far have been quite simple examples, but the next example I'm going to give is a lot more complicated, and it regards Japanese kanji numbers. So before we dive into the Scala, let's just dissect the anatomy of a Japanese number. So the most basic unit would be a digit. So here we have 1. Here we have 1, and then we have 1, 2, 3, 4, etc. So that's the most basic unit. But what about, after 3 it gets a little bit more complicated. And then what about if we want to have a larger number, more than 10? So let's say we start off with 1. What about if we have 10 followed by a 1? Well, you might be able to guess that this means 11. And what about if we want to have multiples of 10? Well, if we have 2, 10, 1, then this means 21. And then if we want to add hundreds, same kind of thing. So we've got 300, 2, 10, 1. Then I'm sure you can guess this means 321. And then you can add 1,000. And then we have 1,321. So far it seems quite simple. It's just like a digit followed by unit, digit followed by unit. But when you get into the larger numbers, it gets a little bit more complicated. Because let's say, for example, we start off with this. So you might be able to tell already that this would be 3,200. But then what if this is then followed by 10,000? Then this entire block is then modifying the 10,000. So you have 3,200 times 10,000. So this is actually 32 million. And then that can also be followed by other numbers. So then, for example, go the wrong way. Then you'd have a 32,002,000. So, and then also there's an even higher unit, which is 100 million. So then this could then be modifying 100 million. So basically what you end up with is this kind of nested structure of all these number blocks that are modifying each other. So how are we going to write a rewrite rule for this? So first of all, let's consider this very large number. And I appreciate that most of you can't read Japanese, but the units are written in blue, and then, the digits are written in blue, and then the units, like 100, 1,000, they're written in red. So in order to preserve this kind of nested hierarchy of numbers, the first thing we want to do, we would want to start from the lowest possible unit, which would be a digit. So we'd want to transform those into numbers. And then we want to go to the next smallest unit, which would be tens. So here we have a 10 and a 3 and a 1 either side of it, and we also have that here. So then we want to rewrite those. And then we want to move on to the hundreds, and then we want to move on to the thousands, and then we want to move into the 10,000s. So we want to go up in from smallest to biggest in order to preserve this kind of nested structure. So we might go about writing a rewrite system as such. So for digits, it would be just like English. This character, we see this, make it number 1, etc. And then for tens, we're going to devise various rules for if we see the character for 10 preceded or followed by a number like that. And then we'll do the same thing for 100, and so on, and 1,000, and so on. And let's try applying this. So we have our large number, and we have all of our chained rules. And let's see what happens. Unfortunately, it didn't work very well. So as you can see, in the first pass-through, the digits were converted into numbers successfully. But then after that, we just kind of end up with some sort of nonsense output. And the reason why is because this is not confluent. Let's take a deeper look at what's happening here. So firstly, it's translating the digits into numbers perfectly fine. But then what it's doing is it's starting from the beginning of the string, and then it says it sees 3 followed by 1,000 followed by 2, and then it's going to look through our chained list of rules, and it's going to go Japanese digits, nothing matches here, Japanese tens, nothing matches here, Japanese hundreds, nothing matches here. Then I'd be like, oh, Japanese thousands. And then it'll preemptively make that into a 3002. And then each number like that is basically skipping ahead in the chain of rewrite rules and preemptively applying it. And so we just end up with this sort of nonsense list of random numbers. And the reason why is because this system is not confluent. So the order of the rules applying matters. And in this case, they're not being applied in the correct order. So how are we going to fix this issue? So I think there are 2 approaches. One, which was my first approach, would just be to change the implementation of the entire system so that you strictly only apply one rule at a time. So something like this. But this didn't really sit well with me because I had to sort of change the behavior of the entire system just to incorporate some rules that weren't being applied in the correct order. So the second approach would be to actually make the non-confluent rules confluent. And generally, you can do this by embedding extra information into the rules. So instead of just using the case class number, I'm going to use various case classes that express what position we are in what stage we are in the calculation. So let's return to our rules. So when we start off with the digits, we're not going to convert this into number. We're going to convert these into number 1. This represents that we're at the first stage of our calculation. And then for tens, we're going to make rules for whatever 10 is followed by a Japanese number 1, or etc. And then these are going to be converted into number 2s. And then the same thing for hundreds, thousands, each going up in one stage. And then right up to 100 million. And then and only then, we're going to convert into a number after everything is finished. So let's look at actually applying this to the previous number. And as you can see, it starts off and it goes in the Japanese number 1, Japanese number 2, 3, 4, and it combines the number in our desired order. And there are other rules that I haven't mentioned here just for the sake of saving time, but for example, English word numbers. So if we have a number that's written out as a word, like 121, then this actually requires a similar approach to the kanji numbers. So like an ordered approach with the different case classes and with some extra steps to remove commas and hyphens and the word and mixed Arabic and kanji numbers. So, for example, if we have 12 followed by 10,000, this also required a similar approach to kanji numbers. And English months like January, February, this is like rather trivial. So, yeah. And so, as you can see, we had this mixed list of characters and entities. So when we want to actually compare the numbers, we're not interested in the characters. So the final thing that we'll do is we'll extract only the entities. And if we return to the sentence that we had at first, on September 13th, 2024, I earned 330,000 yen, then we'll end up with this output. And the Japanese sentence, we'll end up with this output. And this is much more easy to compare. One issue is that in English, if you see 2024, you can't really tell if it's a year or not. But when you're comparing them, you can just say that a number is acceptable output for a year. But yeah, this is a lot more of a comparable format. And yeah, so yeah, here we've seen how I've applied rewrite rules to a named entity recognition problem. And I think that there are probably other solutions that are also appropriate for this case. So I could look into parser combinators, for example, and compare that approach and see which one is better. Or I could even create an add-on for cat tools and charge them money, because I don't know why they haven't solved this issue yet. I don't think it's that hard. But in any case, in less than an hour, we've already written a better system than all of these existing tools that have been in the market for 20 years. So yeah. Thank you for listening.